Hello, today we're going to look at lesson 2.3, 2.4, exponential functions and exponential function manipulation. We're going to address the objectives of identifying and describing the key characteristics of exponential functions, and then we are going to practice rewriting exponential expressions in equivalent forms. We will eventually be constructing models for situations involving proportional output values over equal length intervals. So that's where we're moving toward. So let's start today by revisiting what we know about exponential functions. So far in math, we've studied several different types of functions. We've studied linear functions, quadratic functions, and exponential functions. These functions keep showing up in all the math classes that we have been working toward. For instance, we started talking about linears in Algebra 1 and a little bit about quadratics, and then we studied more of those in algebra, and some of those came to be in geometry as well. And again, this year pre-calculus, but also past pre-calculus into calculus and future math classes. So right now we're looking at these three families of functions, and they kind of pop up a lot, even on SAT and ACT. So that's the family of functions of linear, and then we could be saying it's a family of functions because we could perform all kinds of transformations on that to make and create new functions, as well as the grouping of quadratic and exponential. So exponential functions are some of the most common seen in the real world type applications. They appear in all kinds of places, like when we talk about population growth, where the base might be 1 plus the percentage of growth or 1 minus the percentage of growth, because in population growth, that would be 100% plus more or 100% minus more. And then we might be looking at money. So there are a lot of models with interest and debt, radioactive decay, percent of growth and decay, spreading of diseases. We can use these models to predict a lot of situations and events. So in addition, just so you know, on the SAT, you do often tend to see several questions about exponential functions. So let's start looking and reviewing the key characteristics that you already know or maybe need just a little brush up on. So key characteristics of these exponential functions. So we'll start there. We basically have the general form of an exponential function, which is right here. So that's f of x equals a b to the x, where b is greater than 0. A can't be 0 and b can't be 1. So there are some conditions to be met for that exponential model. We studied and learned previously that that a that's right here in front, that represents the initial amount, and the b represents the base or the common ratio. So nothing new there, basic characteristics. If we have a situation for exponential growth, then that means in our model, that b value, which we find right here at the base, that has to be a number greater than 1. So when it's exponential growth, the graph starts at a low position, and as you read the graph from left to right, you can see that that graph slowly, the y values get bigger and bigger as it moves across. If it's an exponential decay, then we have a situation where the b is between 0 and 1. And so when that's the case, it starts on the left side of the graph high, but as you move on the graph toward the right of the graph, then the y values become smaller and smaller until they approach the horizontal asymptote. So in case you forgot, on exponential functions, right, those parent functions you learned last year, there are horizontal asymptote right here at 0, and that function does not cross that horizontal asymptote. So the horizontal asymptote of the main parent function is at y equals 0. So just kind of refreshing our memory here. So this in case b is greater than 1, but this case b is a fraction. So that's one characteristic, basically knowing it's exponential growth or decay. So if we have a percent of growth, then that b value would be 100% plus the percentage that's getting bigger. So you would represent the 100% as a 1, and if it's growing by 25%, then the base will become 1.25. In this case, the base is a fraction to begin with, so that's what produces the decreasing. And so sometimes an exponential in a financial model like that, where it's like a decay of 25%, then it would be 100% plus the 25% more, but it would be decreasing. All right, so the next characteristic is increasing versus decreasing. So what we know about exponential functions is that exponential functions always increase or always decrease. They never switch from increasing to decreasing. They never have both within the function, which means that this function has no relative extrema. Okay, another characteristic we want to review real quick is concavity. So we can say concave up or concave down. And an exponential function is always concave up or always concave down. It never switches its concavity from one to the other, so there are no points of inflection. All right, the next characteristic we're going to look at is end behavior. So we have been discussing end behavior and reviewing and kind of expanding on what you learned in Algebra 2. So for exponential functions in general form, that's the form that we talked about right here. The x values or the input values increase or decrease without bound. So that's what the input values are doing. As the input values are doing that, the output values or the y values will decrease without bound, or they might approach zero. So those end value behaviors, because of the nature of the function, are either going to approach or increase or decrease without bound, or they're going to approach zero. So as we look at the exponential function, remember you learned from Algebra 2 that it starts way out here in negative infinity land, and it curves up and goes up way up there. It has a horizontal asymptote, so the domain goes from negative infinity to positive infinity. But because of this vertical asymptote, the graph starts here at zero, goes up to positive infinity, but doesn't actually include the zero. So those characteristics, can think about that as we think about end behavior as well. We have been working very hard this year on our limit statements. And so we have limit statements for end behavior. And so in the model here, remember that this plus or minus in front would indicate which infinity that you're moving toward, that what the x's are doing. Here we have the function a b to the x, because remember in our limit statement, we have to have some sort of function to be evaluating the limit at. So if you know the name of the limit, then you can use the name right here. If you don't, you can use the general exponential model. And then it's either going to have the output values approach infinity or negative infinity. And then if that isn't the case, then they can also approach zero. So we're looking at those output values moving toward positive infinity, negative infinity, or zero, depending on the nature of the exponential function that you're looking at, whether it's increasing or decreasing. So now we're going to look at some problems, and we're going to practice being able to identify these characteristics. So example 1, we have 4 different exponential models, and we are going to write the limit statement for the left and right hand side. We're going to determine if it's concave up or concave down, and we're going to determine if it's increasing or decreasing. So based on the characteristics that we just reviewed. So as we look at these models, remember in the graph, that means we have this horizontal asymptote right there. So don't forget that exists when you're describing things. So this particular function doesn't have a name, so you can either give it a name or you can just call it a generic function. So we're going to say the left side is going to be the limit as x approaches negative infinity, because we're going to the left. And then I'm going to use the function a b to the x. And then what is that happening? So as this function moves, as the x's move to negative infinity, what are the output functions doing? They're going to be moving upward toward positive infinity. So then if we do the right-hand side, the limit as x approaches positive infinity of our function a b to the x is going to equal. So as we're moving to positive infinity, the y values are getting smaller and smaller and smaller until they're approaching that horizontal asymptote at zero. So if we look at this particular function, we should be able to see the shape of it. So we should be able to determine that it's concave up. And then is it an increasing or decreasing function? Because remember, it's never going to be both. So as we remember that we always read a graph left to right, we're going to start on the left-hand side and read down our graph, and the y values are getting smaller and smaller and smaller and smaller as we move across to that horizontal asymptote. So we can say this is a decreasing function. So that's the practice that we're going to do. But I want to jump over here to C, and I want to talk about that a little bit, because sometimes if you have a model like this, when we're observing what's going on here, we can see that it has a name, so g of x. So when we're writing our statement here, we'll be able to insert the g of x. And then I can also look at that b value. So the b value is 2/3. So looking at our initial characteristics, if b was 2/3, then this was a decaying function. So it's starting high and going low. So I can give myself a rough graph of a function that might be doing that. That might look something like that. And so I can kind of visualize what's going on as I answer these questions. So when I get to this point, I should be able to write the left-hand statement, the right-hand statement, determine the concavity, and determine if it's an increasing or decreasing function. So go ahead and pause your video, and I would like for you to do part B, C, and D, and then we'll come back and compare answers. So go ahead and pause the video. All right, let's see how you did. So if we start with B, again, don't forget that we have that horizontal asymptote right here. So as you're looking at this problem, we keep that in mind. And then we can say to the left, so the limit as x approaches negative infinity of our function is moving toward negative infinity. So as this graph curves around and it's moving down, the y values or output values are going to negative infinity. As we're moving to positive infinity, then we're going this way. So reading left to right on the graph. So the y values are getting bigger and bigger and bigger until they get close to 0. So in this case, you can see the curve is bending like that. So we know it's concave down, and we know that it's increasing because as you move to the right, from left to right, the y values are getting bigger. On this one, we said we knew it was going to be a decay because the base was going to be a fraction, so it's going to start high, go low. Again, we have that asymptote there we don't want to forget about as we're looking at the graph here and my one I sketched here. So then we can see the limit as it goes to the left, it's going to go to positive infinity. The limit as it goes to the right is going to go to 0. And then I'm looking at the curve down like this. I almost forgot the bottom part. It's concave up. And the y values as you go left to right are getting smaller and decreasing towards 0. So the last one, B, was greater than 1 because it was 4. So that makes this a growth model. And so it starts low and it gradually grows higher and goes steeper. So the limit as you go to the left is going to be approaching 0. The limit as you go to the right is going to be going up toward positive infinity. You can see what the curve would look like there. So concave up, and the y values from left to right as you move across the graph are getting bigger. So it's an increasing function. So hopefully you had pretty good guessing and reasoning through those examples. So make sure you're good with those characteristics. We're going to move on to the next part of our review, and that is looking at some of the properties and exponent properties, because we can use the exponent properties to write equivalent forms of exponential functions. So we can manipulate or rearrange exponential functions for equivalent forms. And we use those properties to do that. So we're going to take a minute. We're kind of going to go through those properties real quick and refresh your memory just to make sure everybody is good to go. So on this one, this is the product property. And in the product property, we are multiplying two bases together, and they're two like bases. And when I multiply like bases, then I can add the exponents. In the examples here, we have one example that uses variable bases. So if I'm multiplying x base and x base, those are common bases, so I can add the exponents. So 5 plus 3 would make that x to the 8th. Here's an example with numerical bases. So multiplying common base of 2, I can add the exponents and I get x plus 3. So that's the product property. The power property is where we have some base with a power raised to another power. Sometimes you hear this referred to as the power to power property. And so what happens when you have that power raised to a power is you have this a multiple number of times based on whatever your n is. So the shortcut here, since that would be a repeated process, is we can multiply the two powers together and then keep that base, but that exponent then would be their power, or their product, excuse me. So here we have a base of x with a power of 5 raised to another power. So a power raised to a power. So I can say 5 times 3, and that gives me 15. Here I have a numerical base. So I have 2 to the x, but that's raised to the power of 3. So that means I have 2 to the x times 3 power. The next property is the negative exponent property. And the negative exponent property is what happens when this particular base is raised to a negative exponent. So we can think about this side of the property like being over 1, and that negative exponent, to make it positive, we change its location in the fraction and we move it to the bottom. So it looks like this. There's one kind of general rule is when you're simplifying with exponents, even in calculus, we don't consider a finished problem if there's negative exponents left in the problem. So we're going to practice making sure we can get rid of those negative exponents this year as well. There are a couple of properties on here that or that aren't on here that I would like to review at this time. So the first one is the zero property, and you can just add it to the bottom here. And basically, you know this, and we've been using this all year already, because anything to the 0 power is just 1. So that's another property that we want to make sure we're good at. Along the lines of the power property, we also have the quotient property. And the quotient property would be if we had like b to the m over b to the n. So I have two of the same bases being divided. And when that's the case, then I can simply subtract them, m minus n. And we do have to worry about order on the quotient property, because remember that subtraction and division are not commutative. So where, we might be able to multiply m times n or n times n and get the same answer because that is a commutative property, we can't do that with a quotient or anything with subtraction. So it is very important when you have this situation to remember that it's top minus the bottom. All right, then there are some other properties that I want to go over, and that's the rational exponents. Sometimes our answer is in rational exponent form, sometimes it's not, and sometimes it's in radical form. So the first one is if it's x to the 1 over b. So when that's the case, you all know that, and we've kind of practiced that because this is one way you could enter a radical into the calculator and save having to go to the math menu to find it. But basically what that means is you're taking whatever that b is, that's the root, and x is inside. So if this is to the 1/2 power, then that's just the square root of x. If that's to the 1/4 power, then it's the 4th root of x. So that bottom of the rational function or rational exponent, the denominator of the rational exponent, is the index. Then the other property that goes along with this is what it looks like when it's not a 1 on top. So for instance, if it was x to the a over b. Well, the b's would still work the same way. So if I go into my radical form, that's still going to be b. But what do I do with the a? Hopefully you remember from Algebra 1 and Algebra 2 that then that a becomes the power on the x underneath the radical. So the b is the index, the a is the power to whatever the base is underneath the radical. So those are two different rational exponent properties. So we have product, power, negative, quotient, 0, and rational. All right, so now I have some practice problems. So here are 9 problems that I would like for you to practice using the rules that we just went over, keeping in mind that we never will consider ourselves to be finished. And that's why there's a reminder here about those negative exponents. So an answer isn't finished simplifying if we have a negative exponent. So go ahead and pause your video and practice these 9 questions so you can make sure that you are good and that you can apply the exponent rules properly and efficiently. So go ahead and pause the video. Okay, let's see how you did. So on the first one, that was the quotient property. So we subtract the exponents. 2 minus 4 gives us a negative 2. Now we have a negative exponent property, which means we move that to the bottom of the fraction, and then I can evaluate it. So at the bottom of the fraction, it would be 1 over 4 squared. which would give us our 16, so 1 over 16. So here again, quotient property, so we subtract the exponents, top minus the bottom. So 3 minus 6 gives me -3. -3 exponent rule says I drop it to the bottom to make that exponent positive. C, we have a -3/2, so that's the negative exponent rule, so we drop it to the bottom to make it positive. Then we have a rational exponent, or in this case, we can turn it into a power to power, because I can break up that fraction. That fraction is the same thing as 3 times 1/2. So if I bring the 1/2 inside with the 100, that's the same thing as saying I can take the square root of 100, which is 10, and then I can raise that value of 10 to the third power, which gives me 1 over 1,000. D is a negative exponent rule, but it's a quantity, so now we have to move the entire quantity to the bottom. So now it becomes the quantity 2 plus 4x raised to the power of 2. Or if you were taking it further, maybe for a multiple choice or something, then you can write this down twice because there's 2 of these binomials and then multiply it together. So you would get 4 plus 16x plus 16x squared in the bottom, because remember, this is not a product property. You can't just distribute that power of 2 through there. You need to physically write that down twice and then do the multiplication. E is e to the 2/3, so we can split that power, that exponent, which is rational, up to a power. So I can say 8 to the 1/3 raised to the power of 2. And so when I take the third root of 8, I get 2, and then I have 2 to the power of 2, which is 4. Technically, you should be able to reverse that, but then if you're reversing it and raising it to the power first, then you're going to have bigger numbers to work with. So I think it's personally easier if you bring the radical first, so you can take that radical, the third root in this case, and get the smaller number of 2, and that's what you're raising to the power of 2. Otherwise, you would be taking 8 to the second power, and then you would have your bigger number. So 8 times 8 is 64, and then you take a third of that. So moving on to F, so we have a negative exponent rule. So to get rid of that negative exponent, then this is on the whole quantity. So technically you could think of that as 1 to the power of -2, and 3 to the power of -2. And so what happens is then to make this positive, my numerator needs to go to the denominator. My denominator needs to come up here to the numerator. So that fraction inverting is going to make that power outside a positive 2. So here's what we have once we move our stuff around, which is the same thing as saying 3 squared over 1 squared. And so 3 squared is 9 over 1 squared, which is 1. But once we kind of get it over here, we can definitely see we just have 3 over 1, which is the same thing as 3. So that's the same thing as just 3 squared. So in either case, we get 9. Then we move down to well, we have some mislettering here, but the second F. And so it's this whole quantity to the power of -1. So we could distribute that power through and have a -1/2, -1/2 using the power to power property, or we could use the negative exponent property, which says we need to move all of this down to the bottom of the fraction. And then we can actually reverse here and take this a step further, because if this was a to the power of 1/2 and b to the same power of 1/2, then this could also have been rewritten as ab to the 1/2, because that's what it would have looked like before we distributed the power through with the power or product rule. So down here, then I can take those a and b's to put them as a product together and raise them back to the 1/2 power. So can you see right here, if I go back the other way, I can say, oh, this is a product in here, so I can take, there's an exponent of 1 on the a, so I can say 1 times 1/2, or there's an exponent of 1 on the b, so I could say 1 times 1/2, and so I get a to the 1/2, b to the 1/2. That's also the same thing that if I have this quantity to the 1/2 is I could rewrite that as the square root of AB. So there's lots of ways you could have thought through or looked through that problem. I just wanted to make sure that you kind of did think about the fact that since both of these had the same power, then they must have had a power distributed through. And so you could reverse that property and look at it this way. And then this letter G, anything to the 0 power is 1. So it might look like a complicated problem, but all of this raised to the power of 1, or power of 0, is just 1. And then we get down to our last practice problem. And so hopefully you can see b to the 0 here, that turned to 1. So on top I have a squared times 1, and on the bottom I have 3a to the 4. So what I chose to do in this one is pull out my coefficients, because the coefficient of 1, the coefficient down here is 3. So technically that's the fraction 1/3 times what was left. And what was left was a quotient rule, because we had a squared on top and a to the 4th on bottom. So I can apply that subtraction and do top minus bottom. That gives me 2 minus 4, which is going to give me a to the -2. And so what I can do with that -2 then is drop it into the bottom of my fraction, and my fraction already currently has a 3 for my coefficient. So I end up with 3a to the 2nd on bottom and a 1 on top. So that's that last practice problem. So hopefully that went well and you felt comfortable looking at those particular problems. Okay, so now we're going to look at a little bit more of the modeling and thinking about different representations. And in this particular situation, we're talking about the same exponent rules, but they can also be used when working with transformations. So since it's exponential and the variables would be up in the powers, we can explore this horizontal transformation of exponential functions. And so what that means is we're going to first start by just practicing looking at what the transformations would be, and then we're going to use our exponent rule to figure out how we can rewrite them. So when I'm looking at this first one, I'm looking at right up here in the power, that's where you see the transformation. So if we were going to say this is a transformation, then what was the original function that we started with before we applied the transformation? So that would have to be a base of 4. And then if you can see the +2 right here, that's the transformation. So I can say my original function, or the part of the function I'm looking at, was f of x. So we could call that and say, that's g of x, and then f of x is the result of the transformation on g of x, something along that line. So I'm just going to try to streamline this so we're really focusing on that. But we could say that we could call this the g of x function, which is the original, and then we can say f of x is the result of the transformation of g of x. So what was the transformation? What does that +2 mean happened? So it was a translation, and it was horizontal. And which way did we go? So it's +2 inside. So when it affects the y, it's opposite behavior. So then I'm going to say to the left. And how many? 2. So the original function, and then what is, in this case, was a translation because we were just sliding it. All right, so let's look at this. So we have 2 to the 3x. So this was function g of x. So we have an original function of what? What was the original function before the transformation had been made? And that would be 2 to the x. So I'm not going to reassign name values here because I really want us to focus on what's happening in the transformation. So I hope this notation is okay, makes sense to you guys. So we're saying g of x is the result of transforming this original function. So what was going on with the transformation? So I'm looking up here in the power, and so I see that we have a 3 and an x. So if x was the original, then multiplying the 3 to x was the translation. So when it is a product, we know that we have a dilation. And what is the dilation that we have? It's a horizontal dilation by a factor of what? Now, before we say the factor, think about this. It's inside the transformation, so it is affecting the y. So we have to remember that that factor is going to be 1/3, not 3. So do pay attention because that is inside. That's affecting the x's, not the y's. Okay, so let's move on to the next one. So here is our function, and the power is x divided by 2. So another way that you could write this, if it's easier to think about that, is you could say this is the same thing as 9, and then it's the 1/2 So it just kind of lets us see that this is still a dilation, but what's happening inside is 1/2. So I can say that we have a dilation is the type of transformation, and what is it specifically? It's a horizontal dilation by and the factor. So remember, the factor inside is 1/2 now. So the factor in that translation then would be by 2. All right, so let's move to this last one, k of x. So we're looking at what's happening in here. Okay, so there's my translation or transformation. And so then we're going to figure out what's happening. So what was the original? And we can say that's 5 to the x. And I didn't actually write the original one on this one. Sorry about that, guys. Original would be 9 to the x. So here we have 5 to the x. So then what is happening inside that piece of the function? So we have a -1 inside. So that's going to be a translation. And then what kind of translation is that? It's a horizontal translation. That means sliding it around. Which way is it going? To the right. And how many is it going to the right? 1 unit. So this stating this in our notes is just that. What kind of transformation? Then I'm deciding what it is. You could basically, if you were asking to list the transformations, you could just go straight to here. All right. So now why is that important? Well, there are a couple of things that I want to look at in here. And the part that's really important is now we're going to be using what we know about transformations, and we're going to be using what we know about properties to do some other things. So first thing is we can use the exponent properties to rearrange the function and put it into an equivalent form. Just like when we applied the properties, we made those into equivalent forms. So in this case, we can use the product property in reverse to show equivalent forms. So what do I mean by that? Well, the base here is 4, and we know from our product property that if I multiply like bases, I add the exponents. Well, if I'm adding the exponents, then that means I had to originally have had 4 to the x, 4 to the 2 in order to be able to add those exponents and get to this form. Well, now I have split this up, and I know 4 to the squared is 16, and 4 to the x just stays 4 to the x. So what happened here is in this first part, the piece right here, we had a horizontal translation. But when we ended up here, we had a vertical dilation. So this means that they're equivalent forms, but we went about the process of using those the exponent properties. And so now the equation that we started with right here no longer has a horizontal translation. It has a vertical dilation by a factor of 16. So that's kind of interesting how we can use that property to rearrange the problem and come up with an equivalent version of that exponential function. So that's what we're going to do right now. We're going to practice that property. It's actually something that we use quite a bit in calculus, so it's really great that we're practicing that. So when we look at this function, f of x, we can see that that's 2 to the x plus 3. So we know that we applied that product property. So that would have been 2 to the x, 2 to the 3. And so now that we have applied that product property, we know we can rewrite that as 2 to the 3rd power, which is 8. And then we're left with 2 to the power of x. So it started out as a horizontal translation. It ended up as a vertical dilation. So go ahead and pause your video and practice B and C to make sure you're good using the property to rewrite those statements. So pause your video. Okay, so let's see how you did. So we split this one up as 3 to the x, 3 to the -2. 3 to the -2, we can't evaluate it as it is with the negative exponent, so we're going to do 1 over 3 squared, which gives us the 1/9, and then I'm left with 3 to the x. So that's my vertical dilation by a factor of 1/9. Here we had 4 times, and then we can break this up. 3 to the x times 3 to the power of 2. 3 to the power of 2 is 9. 4 times 9 is 36. 3 to the power of x. So now our vertical translation, the vertical dilation is by 36. All right. So we can also use, we're using the product property here, but we can also use the power property of exponents to rewrite with. And then we can show that every horizontal dilation of an exponential function is equivalent to the changing the base of the exponential function. So the horizontal dilation, and we're going to be changing that base to that function. So what does this mean? This means that if I use the power property, so I start with this function, which is f of x, and that's b to the product cx, then I could rewrite that using that power property, and I can split the c and the x up. So I can say b to the c, get that answer, and raise it to the x. So I can change the form of that around as well. So we're going to apply these two properties in the last two examples that we're going to do. And so in the first one, so if we do our read here, first read here on example 3, which of the following functions is equivalent form of the function y equals 9, and the quantity is a product for the power of 2x. So you're going to manipulate this using your powers and figure out which one of these is the right answer choice. Then we're going to look at 4, and it says which of the following is an equivalent form, and we have y equals 9 times 4 to the x. So then, which of these would be an equivalent form to that? So let's go ahead and pause our video, and I'll give you some time to work on example 3 and example 4, and then we'll come back and compare, and we will have finished the lesson, and we can talk about our takeaways. So pause your video and work through example 3 and 4. Okay, let's see how you did. So I was definitely using the product property here because I had 9 and then I had a product within the power. So then I said y equals 9 to the power of 2 raised to the power of x. So 9 squared is 81, 81 raised to the x power. So that eliminates A, B, C, and leaves me with my choice D. On example 4, I worked backwards. So here I had what was going to be the simplified version. So I wanted to work backwards and see which one would match up. So I took this one, and this is the same thing as 1/2 times x. So I raised 16 to the 1/2 power and raised all of that to the x. Why I chose that order is because we know that 1/2 is the square root and 16 is a perfect square. So the square root of 16 is 4 raised to the x power. The A number was 3, definitely does not match 9 times 4 to the x. This one had a product at 16, so I did the power again, 16 squared to the x. That's going to be a crazy big number, not going to get anywhere close to 4, so I ruled that out. When I went to C, I split it up again, thinking of this as 16 with the power of 1/2 x. So I raised 16 to the 1/2 and raised that to the x, much like I did in part A. So the square root of 16 is 4 raised to that x power, and I had a 9 coefficient, which is what I was looking for right here. So C was my choice, and I could easily have ruled D out as well because the same thing is true as what we did here. So we had 9 times 16 squared to the power of x. And so that's going to give us a really big number, which is not going to get us, again, anywhere near close to 4. So those are practice problems, kind of looking at how we can use those exponent rules to do different things, manipulate and rewrite statements. This can become important, very important skill, especially if you're looking at multiple choice questions and you get an answer, but that's not really the form you see the answer in. So we want to have ways to be able to address that. We talked about in 2.3 key characteristics of exponential functions. So we talked about the exponential function in general form, and we talked about b can't be 1, a can't be 0, b's got to be greater than 0, and it's got to be in this form, a, which is the initial, and then b to the x. We talked about growth and decay models. So when that b value is greater than 1, then it's going to be a growth. So you might even think of something that some of the things you did in Algebra 1 and Algebra 2, where you talked about percentage of growth. Or if it's had a 10% growth, then that was 100 plus 10%. And so the base would be, the equivalent. So growth means base is a whole number and it's growing or getting bigger as your input values get bigger, the output values get bigger. And then decay, it looks like the same model. However, this b value in here is going to be a fraction. It's going to fall between 0 and 1, which makes it a decay model. So it is going, all of the output values as the input values get bigger are going to get smaller. We talked about the domain and range of exponential functions. So the domain goes from negative infinity to positive infinity, and the range goes from 0 to infinity. But notice it doesn't include 0 because that's where that horizontal asymptote is. We talked about the fact that exponential functions are always increasing or decreasing. They never switch and have both. So you won't have an increasing piece of the graph and a decreasing piece of the graph when you're talking about exponential functions, which means there is no relative extrema on these functions. When we talk about the concavity, whether it's concave up or concave down, it's only one or the other. It can never switch between concavities within the graph. Therefore, there is no point of inflection. We talked about end behavior and limit notation. So as the x's or the inputs increase or decrease without bound, the outputs will either increase or decrease without bound, or they might approach 0 depending on the function. Then from the 2.4 takeaways, that's where we were practicing all of our exponents and being able to change the forms of the model and being able to take a horizontal translation and change it into a vertical dilation by applying the properties like we did here. And then we talked about all the other exponent properties. So the product property, the power property, a negative exponent property, quotient property, the rational exponent property, and I just put the m over n1 here because remember if m is 1, then it's just v to the power of 1 inside. And then finally the zero power property, which is anything to the 0 power is 1 except 0. So you have some daily practice to work on to practice, make sure you can apply all of these rules, and I will see you back here next time for our next lesson. Thanks so much, guys. Bye.